Hello everyone and welcome today in a webinar. In this session I'm going to tell you how to model a concrete tunnel and do the Young hardening analysis and control the developed temperature through the cooling pipe elements. A quick overview about the geometry of the model. This is a symmetry model. This is a concrete block and there is another segment is here. Because of the symmetry we only consider the right part. And these are the cooling circuits that are basically supposed to control the developed temperature. What we are going to do, we're going to define this section for the wall, we're going to define the section for the slab, we're going to extrude it, make a solid model, and also define these circuits based on the polyline feature. In terms of the cross-section, you can see these solid points are the inlet for our coolant fluid. These arrows are representing our convecting boundaries, so you can see everywhere is convecting boundary except the symmetry part, and there is no exchange of the temperature with ground. So let's get started and do the modeling part in Diana. So we open Diana and make a new project. I define the name of the project, Young Hardening Concrete. I select the type of analysis, structural and heat flow, three-dimensional, and leave the rest as default. Let's check the units. For this particular analysis, for the input we keep it as a second. Later in the analysis setup we're going to define that as a day, but here I change that to Celsius and we are good to go. So let's start with the first panel for wall 1. Either you can input basically this coordinate manually, or you can refer to one of the Excel sheets or some reference parameters or data that you have. I already defined that. Wall 1. If I go to geometry, you're going to see that. I create the second wall. And again, read the coordinates of this panel from Excel. What I'm going to do, I'm going to do multiple array to make several of these segments to create part of my section. So I'm going to select multiple array, select these two, copy it in the Z direction with relative displacement of 0.5. 4 times, click OK. I need to make bigger panels here, and for that again I can go to create this wall 11, copy that. I'm gonna make another one, wall 12. So we have this. I'm gonna do another multiple array, so this time based on these new segments. Again in the direction of Z, but with the relative length. And this time it's 2 more times. So I have the model. Then there are 2 more segments that I need to create. I create a sheet, wall 17, I can copy that, click OK, another one, wall 18, so I have my first segments ready. What I'm going to do, I'm going to copy this strip and bring it to the right part. So select this, select the strip in the X direction, 85 one time, click OK. So you can see the wall section is ready. The next step is creating my slab. create another one. And once again, I can bring the reference coordinates from slab. Click OK. So now you can see my cross-section is ready. What we can do here, we can proceed with extrusion. So I can go through extrude, can select everything in the Y direction, 20 meter. So this is my solid body. And what I need to do now here, I need to extract 2 lines from the bottom part of my wall and make the imprint on the literally slab. I change my selection to line. I click these 2 so you can see these lines, the red ones. I just right click, extract, and you can see these 2 are available there. So what I need to do, I need to change to the body, hide all, make slab and lines available. So what I'm going to do here, I can imprint their position. The face, this one, and here I can just simply go through. So I have an imprint of the wall on the slab, and what I'm going to do here is creating my cooling circuits. Circuit 1, make sure that this is off. You can see the model. So what I'm going to do, I'm going to copy this, in the X direction, and I'm going to create again another polyline, so this time is circuit 3. Make sure that this is off and click OK. So I have my model, I have position of the slab and the rest of the segment that's gonna be active on the model. So what I'm gonna do here now, I'm gonna define a boundary condition as a kind of environmental or external temperature to the model. So to that purpose, I click here in the right view, define environment temperature on the faces, and we are talking about the external temperature, which is 15. And what I'm going to do here, I am going to select this face, all the faces on the side, on the top, and this. So you can see all these solid colors or dark colors are subjected to the 15 Celsius, nothing assigned to the symmetry and nothing to the bottom. So the next step for us is assigning boundary heat flow boundary elements to the model. So for that, again, I change the view. I go here, I define boundaries. I define boundary interface. So from the face, again, I select the lower one, the upper one, this one, this one, this one. So all these going to be my boundaries. What I'm going to define here, I'm going to define as a heat flow boundary and assign material properties. So in terms of the interface and heat flow boundaries, I define thermal effect. So what is the value here? 14 and OK. So you can see the boundaries are generated automatically under the geometry part. So what else we need to do? We need to assign or attach the initial field to the model. I hide my circuit. I go here. I say initial concrete. I'm going to select all these. Temperature 10, and this is my initial temperature in the concrete. There are some inputs for the material properties that we're going to do that together. First thing, I'm going to assign different type of material property to the wall and another one to the slab. So now we are going to assign the material property to the wall, the concrete part. Selecting upper part, this is the wall. This is a structural slab, structural solid. We're going to create a new material property for that. Then as a material property 310, for conductivity and capacity. We're going to define adiabatic curve. And close. Now I'm going to repeat the same, this time for the slab. Also for slab, and we are going to deal with the cooling pipes. So what I'm gonna do is I'm gonna select my cooling pipes and show only. Cooling pipes. I'm going to define a new property for them. The concrete masonry. And the type is cooling pipe. Thermal effect. So, what we need to define next, to define the geometry property. This is a perimeter of the pipes, and literally these are our cooling pipes. To select starting point, we're going to select these 3 points. What would be our temperature? Initial temperature in the model. So we have all these in place. Find the mesh, select everything, element size, now we are going to the analysis phase, transient heat transfer. Then what we're going to do here, we're going to go to the initial condition. We define our initial condition. That today our time, and then we go for step size. Okay. We're going to define some output selection. What we're going to define here, temperature for the cooling pipe, this one. So we are good and ready to run. So after performing the analysis, we are going to see the results starting from degree of reaction. For settings and cutting plane, we go to the contour plot. We change the specified values, some sort of a range between maximum 1, minimum 0. We enable the cutting plane, and we can go through the time steps, and you can see the degree of reaction inside the model, different time steps. Another thing that we're going to show here is basically the temperature. For temperature, what we're going to do is we go to the nodal results, temperature, and for the time steps, we can go for the time step 2, and we change the settings, this time between 10 and 20. So you can see the developed temperature inside the model. We can increase that even more. And you can go through the time steps. The another output that we are interested in is the temperature in the cooling pipe. So for that purpose, what we are going to do, we're going to select the cooling pipe output, and we're going to change these settings . 1020, and we're going to disable the cutting plane. So here you can see how the temperature in the cooling pipes are changing with respect to the hydration process. So this was a quick overview about the results, modeling, and the interpretation of the analysis results. Hope you get some idea and you could reproduce the same type of analysis for your projects. Thank you for your attention.